me from the introduction. So yeah, today's topic is code profiling. I particularly wanted to teach this lesson because this was the most helpful for me from Code Astro when I was a participant, and I got a lot of use out of it for my own research. So yeah, the topic is quite dear to me. So let's get started. Um, so what is code profiling? So code profiling is a dynamic way of analyzing how your code performs. Dynamic in the sense you are analyzing how it's performing while you run it. And the focus is on recognizing aspects like runtime, memory allocation, and function frequency. I don't know if you can see my cursor. So I also don't want to use it too much because I go circle, 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 and then that's can be a bit confusing. But so these are the things that usually you want to assess. And we want to do this because we want to improve the performance of our code in terms of, again, time and memory. So it's very essential to identify the bottlenecks. So this is usually a very niche thing. Um, when you have a simple Python script, you don't necessarily want to worry about something like profiling your code. But when you have a large software and you're adding some new code to it, or in general, when you're writing a whole package, you want to identify the bottlenecks in terms of time and memory. Um, so there are so many different tools to do this. Uh, for this lesson, we'll focus on a simple Python profiler, which comes as a part of Python standard library. So you don't need to install anything. It's called C profile. The C prefix is to denote that it uses a C code to do this kind of analysis, and it only focuses on the runtime and execution frequency of all the functions, not the memory allocation. You'll have to use a different tool for that. Let's understand this through an example. Before we go into that, I just want to point out where you can find this notebook. So right now I'm in this folder, Code Astro Day 4. As you can see, there is this notebook, and there's also some two relevant files. So to run a C profiler, first what you need is a script that calls the functions or a class that you want to profile and understand the bottlenecks of multiple times, because sometimes depending on your input parameters, um, you might get different variations of it when you run it just once. So you want to call it a couple of hundred times, so it sort of averages out. And also just to make sure when you call these functions, sometimes the inbuilt functions, the Python inbuilt functions end up coming at the top of the list when you list them by the order of, say, most time consuming. So you want to make sure the relevant functions are the ones that are taking most amount of time. So yeah, you just want to run it a couple of hundred of times at least. So in this demo, we are going to use the package Arbitize. You might be familiar of it by now. So I have this. Mess this up. So this is the script we are using to analyze this function driver. It's essentially some kind of orbital fitting, and it inputs reads some data file, and then it also has all these parameter inputs. So the main thing here is it's calling it, say, 1,000 times. It's running 1,000 orbital fittings, and yeah, it's creating an object and calling that. And another thing is the number of cores is set to 1. I'll come to that in a minute. So um, sorry for moving the screen too much. Why we set the number of cores to 1 is when we do some this kind of profiling, we usually focus on figuring out which part of your code actually takes longer, not necessarily the time bottlenecks induced due to some kind of parallelization, say how delays due to interacting between different cores or threads. So that's not the focus. And if you, so I, something like orbitize, you can turn it off by setting the number of codes to 1. But say you have some code where you can't get rid of the parallelization at all and you still want to profile it using C profile, then you'll have to create a C profile output for each of the processes and combine it using a different command. So to do this, once you have a script like this, profile .py with short function calling the function you want to analyze, you just run it like a normal Python program, Python and then the file name. But now you have two different arguments. The first one is this -m C profile. So what it's essentially doing is instructing the interpreter to also attach some kind of probes to your Python script and start, noting down how long each function takes and how many times they're called, etc. And we are also attaching this argument, which just writing it to an output file. If you don't do this, it just dumps the output into the terminal and we can't probe it later. So we want to save it into a text file so that we can create some nice reports out of it. So yeah, let me just run that function, that command. So you just do this. We'll go through this in the activity. You just need to do this, and it will take a while to run this, and it will generate an output file, something like this. It's a binary file, so you can't really, it's not human readable. But thankfully, Python also comes with a standard library called, it's part of standard library, a module called pstats. So you can use that to probe this output file. So here we are just reading it in and creating an object called mystats. So now we don't need to wait for the thing to be over because I already did it. Let me just close this. Yeah. So yeah, once we create this mystats object, let's yeah, try to um, do this command. So what it's essentially doing, it is sorting it by time, and I'm asking it to print 15, top 15 of those functions. 15 is arbitrary. It's just we don't want it to print out every other output possible. So let's closely look at the output. So as you can see here, it's indicating there were around 16 million function calls, even in a simple script like this one, which only took 100 seconds to run. There are so many function calls happening. But the number of functions themselves that were called is around something 9,000 something. And it's saying in the display, it's restricting it to 15 because of the restriction. And you can give multiple restrictions. And it's also saying it's ordered by internal type. And let's look at these different columns that it's outputting. So the first column is ncalls, which is the number of times, say, this particular function, Newton solver wrapper, was called 4,600 something. And then there is this column called total time, which is the time it took to execute these function, this particular function, excluding any sub functions that were inside this Newton solver wrapper. And per call is just this total time divided by the number of calls. So essentially, how much time it took per one for executing that function once. Here is another time quantity. So it's slightly different from total time in the sense that this now includes how much time it took to also run the sub function inside it. So in case of, say, Newton solver wrapper, both cumulative time and total time are almost same, 28 seconds, something. But in case of this function, calc orbit, for example, you can see that the cumulative time is around 69 seconds, but the total time is 24. To explain this a bit more, let's go to this calc orbit function. So it lies in this script within orbitize called Kepler.py. So this is the function. So when we are calculating something like the cumulative time, we are looking at the overall time it took to execute this whole function. So here it also has, like, say, these sub functions. I hope you can see my cursor. Yeah, uh, calculating mean anomalies and so on. So cumulative time includes all of that, but total time would just indicate the time it took to execute these operations, essentially variable assignments and for loops, or all these algebraic operations, multiplication, subtraction, addition, etc. So yeah, that is the main difference between these functions, between these terminologies. The main use is that, say, if you see a function like this, calcorbit, which has higher cumulative time but lower total time, what it's saying is there is some function inside calc orbit that you're calling that is causing much more delay, that's taking up a lot more time. So you might want to go look at what function, subfunction that is. But in case of something like Newton solver wrapper, because these times are almost equal, 28 and 28, essentially the things you're performing within the function, all these operations, for loops, variable assignments, those are the ones taking the most time. So if you want to speed up something like Newton solver wrapper, you want to go look at those operations. We'll take a closer look at this in the activity. Before we break out into the activity, I want to quickly talk about multiple filters you can apply using print stats. So here I've applied an additional filter compared to the previous one. It's called NumPy. So now what it's doing is it first, so let's look at the output here. So there were 9,000 something functions. Out of that, because of the NumPy restriction, it's reduced down to 680. It's essentially just filtering out all the NumPy functions. And now, out of those, it's printing 15 of them. So it goes from 680 to 15 due to the restriction 15. And this order matters. For example, in this one, I first printed out, I've asked it to filter top 15 of the functions based on time. And then I'm trying to filter it based on NumPy. So first, 9,000 to 15, and then 15 to 1. So you only get one output. So yeah, that's, I think, everything you need to know. So we have this activity, and you can post the answers on Piazza. I hope everyone can see the post on Piazza. So yeah, in this activity, just everything we talked about, go to this folder, run this command, and just answer these questions. You can just, in your answer, just name 1, 2, 3, 4. Yeah, and also I'm here if you have any question about the activity. So I expect this to take around 20 minutes. So we can start posting in like 20 minutes on Piazza.
Mm-hmm.
So yeah, the first one, which function takes the most runtime, not including calls to subfunctions. You want to look at the function that is the max total time. So you just sort it by total time this way. And if you go over here, at least on my laptop, it's the Newton solver wrapper, which has the highest total time. Next one is which one takes the most runtime, including calls to subfunctions. Then you want to sort it by cumulative time. Um, so one common mistake is you usually, if you just sort it by something like time, and then you have like 20 outputs, and if you just go over the highest cumulative time here, you can probably see that calc orbit comes out as the highest cumulative time. And that's, something that usually we do. But to make sure you are getting the highest cumulative time function out of all the 9,826, just sort it by cumulative time, and you should get the. So, like someone asked, there are some built-in functions that take a lot more time. It's very system dependent. But yeah, so we can't speed that up. So we want to look at the orbitized ones. So this is the one. Run sampler is the one that takes the most runtime, including calls to subfunctions. And then next, we want to look at the one that is called the most. Um, so to do this, you just sort it by number of calls, and I'm just restricting it here to 3 so that it all fits into the same single screen. So yeah, in this case, you can see that it's this one, this function. It's some built-in function which is asking is instance. It's like checking that, and yeah, that's called about 1.5 million times. So yeah, that's the answer. And if you want to specifically look at the orbitized one, you add this additional condition, orbitize, and then restrict it to how many number you want. And then with that, the answer turns out to be with for this particular run, I have both transform samples and raw samples. Both of them are called 9,000 something equally. So yeah, the answer can be either one of them. So that's the third question. And so the answers so far have been, um, I don't know if this is very confusing to scroll through it, but yeah, Newton solver wrapper for the total time, and then run sampler for the cumulative time, and draw samples or transform samples for the number of calls. So out of these 4 functions, the one you would likely want to speed up is the one that takes the highest total number of time. Because like I said, if it takes the highest cumulative time, then there is some other function inside of it, which is actually taking the longest time. So, if you try to just speed up, say the answer, the highest one for cumulative time, sorry. This one. If you think of speeding up run sampler, then you'll probably run into a sub function inside it, which is the most time consuming. So there's no point in trying to speed up run sampler itself. So, you want to pick something that has the highest total time, because that has, something like Newton solver wrapper, which has all these operations inside of it, or variable assignments that you would want to speed up. So that would be the function you ideally want to speed up. And yeah, just some simple calculation so this numbers are a bit outdated because I don't know, this time it ran for longer. So yeah, essentially if you speed that up, twice, say the total time was 71 seconds, the overall script, and here it's slightly different, but yeah, like say Newton solver wrapper took 18 seconds. By speeding it up, it only takes 9 seconds now, and then the total script would take 62 seconds. So yeah, so here is another activity. I don't know okay, maybe, yeah, maybe we won't have enough time to go over it. So I'll just leave it up to you to do this, but I'll explain a bit what's happening here. Yeah, so in this activity, we want to probe, say, like we looked at in the previous example of, say, there's a function that takes highest cumulative amount of cumulative time. How do you probe the subfunction that is actually taking the longest? So for that, we have this example. See this function. Sorry, you want to probably do something. Start. Sorry, can time dot stats. Yeah, let me just, So yeah, if you look at this log L function, it has very negligible total time. So it doesn't have any operations inside itself, like that's taking the longest time, but it's calling some subfunctions which are taking much longer. So we want to probe which function's the real culprit here. So how we do it is we can use this particular uh, um, func- uh, function called print callies. So what it does, it prints out all the subfunctions of say log L. Um, yeah, and you keep on doing it. So you say you do this once. I'll just show this one. So you call this my stats print callies logl, and it prints out all the subfunctions it's calling. And as you can see, there's something inside of it which is taking the total like a very long cumulative time compute model. So, and then you keep on probing it until you reach the end where, say this is the last call. You keep doing it, and if you go to the end, sorry. Um, yeah, so when you ask the calc eccentric anomalies, this function to print all the subfunctions inside it. So these are the subfunctions inside it. And as you can see, this Newton solver rapid, the total time and the cumulative time are same. So it has a lot of operations that are taking a lot of time. And so this is the function that's the real culprit, and you want to speed that up. So yeah, that's I recommend trying this out yourself. Even though I already walked you through the solutions, it might be fun to just make sure you're getting there on your own. And for this another activity, let's see. So like I said, print callies calls all the subfunction inside a particular function. But what if you want to see which function creates the most number of arrays? So that can be done with this function called print callers. So this is calling all the functions that were executed that had a numpy array inside it, and this can be done. And yeah, there is a little bit more activity, like some calculations that you can do. So yeah, again, try it out on your own. Yeah. Before we wrap up this session, let me talk a bit about, now that you have identified which function you want to speed up, how do you speed something up? So there is no straightforward single formula to do this. It's usually really, really hard to even get a factor of two, speed up. And these are some common ways people do it. You eliminate any computations that you're not using. We all have the tendency to, do a bunch of calculations that might not necessarily be used in, the function. So remove those and use NumPy functions wherever possible for matrix operations, because NumPy people are spent lots and lots of hours trying to optimize it for this specific use case. And avoid using for and while loops, because they usually take a lot of time. Each time it iterates, there's a condition and it's checking that. To demonstrate that, there is a simple, quick code here. So in this, the goal is there is an array. So both of them are same array, just by different names, um, for demonstration purposes. So what we want to do is we want to add 5 to each of the elements that are greater than 6. So the most intuitive way we can think of is just run through each element within the array and check if it's greater than 6, then add 5 to it. So that's the most intuitive way to do it. That involves a for loop, but this would take much longer. A very numpy way to do this is to create a masked array. So say this one, it basically creates a true false element for all the shape of the array 2 here. And you can use that, and using that master array, you can add 5 in a single step. So yeah, something like this is much faster. I haven't timed it, but again, in array size as small as this, you won't see much difference in terms of time. But when you have an array that is like 1,000, 10,000 elements bigger, then you'll start seeing very considerable difference. So yeah, that's one strategy. And another thing is, if you're using MKL or BLAS inside an already parallelized code, that tends to slow it down. You can disable it. There's a lot more on parallelization in day one material. Please go have a look. And another common strategy is if you're using some kind of iterating function where you have set some precision, and for your needs, if 0.1 precision is good enough and you have set it to 0.001, that's not as useful because it's gonna increase the overall runtime of your program. So think about how precise you want your outputs to be. And we tend to copy a lot of variables. You know, that's like I do it a lot too. But really think about it whether you want to make multiple copies of the same variable, because that takes a lot of time and also memory. And another, I would use this as a last resort. If your Python, you've tried all these things and it's still taking a long time, write a C version of that code and then use a Python wrapper to interact with it. So yeah, there are probably many more ideas, but these are all the ones we have. And then final comment on, okay, let me just zoom out and let's appreciate this meme. This is a very old meme, but still very relevant. Um, yeah, we all do this, spend hours together to speed up something by just 10 seconds. Um, okay. Um, Yeah, and two other comments on this is when it comes to picking the function you want to speed up, say there is a function that takes 50% of your runtime, and if you speed that up by a factor of 2, you're speeding up your whole program by 25% of the time. But if there is a piece of code that only takes like 10% of the time, if you speed it up, you're getting a 5% improvement. So you have to really think about whether it's worth it, because it's not very trivial, like I said, to speed up a function, and you'll likely spend a lot more time than that 5% improvement you got. And another thing to keep in mind is readability. Like I said, if we want to save up the time, we want to avoid something like creating multiple copies of a variable. But that might result in like a very less readability. That has a long-term cost of its own, because that leads to a lot of bugs and it's harder to maintain and fix. So then you end up spending a lot more time on it. So yeah, there's always this readability versus speed up to think about. Yeah, so there are some extra comments related to runtime memory. I won't go over them. You have this notebook with you. So yeah, that's the end of our lesson. I hope you enjoyed it and it's useful. It was super useful for me. So yeah,